So now getting a chance to look at the parameters themselves here. Are there any questions about the structure of the exam or about what you're going to be asked to do? All right, I'm going to assume that that silence means no. So with that in mind, then let's go ahead and I will open up the, I'll open this up to everybody. If you have a question, if you have something that you want to go over, now is the time to bring that up. If you want to look at specific items from any of the review guides, any of the old practice tests, we obviously can start with those. If you have some more general question, we can go from there as well. All right, Caitlin, you had a question?
Yeah. So for the 20 multiple choice, like, what should, I know you said concept, but along the lines, like, what should we expect with the multiple choice?
So I would anticipate that in terms of the multiple choice, you should expect to see things along the lines of definitions, um, general kinds of overall concepts involving. So, for example, we just did that unit on gases. So instead of calculations using the gas laws, a concept question might be along the lines of what is the relationship between pressure and volume? What is the relationship between temperature and pressure? Something along those lines. In some of the other ones, it could be some things along the lines of what is the oxidation number for this substance? Which one of these molecules is polar? Things of that nature. So, as you're going through the chapters, what you'll see is that the weighting here is much more on the first half of the semester. The first half of the semester was much more conceptual than the second half of the semester was. So you're going to see a considerably larger number of chapter 1, chapter 2, chapter 3, chapter 4, chapter 5 kinds of questions in that section. There will be some chapter 7, 8, 9, or 7, 8, 9, and 11 and nuclear questions on there, but they're going to be, again, they're going to be concept driven, and those weren't very concept driven chapters. The whole chapter on stoichiometry, other than balancing equations and identifying types of reactions, everything was quantitative in that one. So if there are questions from chapter 7, they're going to be along the lines of balancing and excuse me, balancing, identifying reaction types, those kinds of things. All right, does that answer your question?
Yes, thank you.
All right. Yeah, so yeah, I understand the multiple choice section is probably the biggest wild card of the group in terms of knowing what to study, because it is just content knowledge. It is not calculation based. You can't throw an equation at the wall and hope it's the right one and plug in the numbers. But at the same time, one thing you should know is that of all of the points, there's going to be about 100. I think I told it it's 155 points. Again, it's about a double exam. So of those 155 points, only about 30% of them are actually on the multiple choice section. The majority of the points in the exam are in that other section, the latter parts of the exam. All right. All right, so I'm gonna mute my video just for a minute here because you can't see me anyway. Are there other questions that I can answer for you at this point?
Yeah, could you go over like redox reactions and oxidation numbers and stuff?
Sure. All right, so when it comes to oxidation numbers, there are really two different types of questions that could be asked of you. We could do the oxidation number slash oxidizing agent, reducing agent kind of question, or we could do balancing. Those are the two primary areas where we could potentially ask you questions. Now, obviously, one of them is considerably harder than the other, but let's start with kind of the fundamental concept, and then we can kind of use that as to drive the rest. So let's just say that I've got a redox reaction, and for that, I'm going to pull up one of our practice tests. So we've got permanganate reacting with chloride to make chlorine and manganese ion. And so the first thing that we're going to look at, and no, this is not on any of the practice exams. I just made this one up myself. We'll come back to do a couple of other examples off of one of those later. I had to wait for it to load up in the background here. But anyway, we could look at this from the standpoint of we need to assign oxidation numbers. Now remember, for oxidation numbers, we had the two fundamental ideas. First of all, the sum of the oxidation numbers had to equal the charge on the substance. That was the first thing. And the second thing was that there were certain substances that seem to always have the same charge. So from that perspective, we could assign oxidation numbers relatively easily in some of these cases. So in the case of the chloride is a monatomic ion with a -1 charge, so it's got a -1 oxidation state. The chlorine is elemental. Elements have no charge, so their oxidation numbers are 0. And for the manganese 2 here, it's a monatomic ion with a +2 charge. It's got a +2 oxidation state. Now, the permanganate's probably the most difficult one of the group because in it, we've got a manganese and we've got 4 oxygen atoms. And together, they make up a -1 charge. But if we use this second rule, we can say that those oxygens are -2 each, which 4 times -2 would give us a -8. And if I followed the algebra all the way through, that would mean I have a +7 on the manganese. Along with the -2 for the oxygen. So with this little bit of information, we have figured out the oxidation number part of the problem. Now, to satisfy the oxidizing agent, reducing agent part of the problem, what we would have to do is we have to look at how are the oxidation numbers changing? What is changing? And so if we do that, we look at the manganese. The manganese was +7 there and +2 there. So manganese is going from +7 to +2. Now, what does that mean for its oxidation state? Is it increasing or decreasing?
Decreasing.
It's decreasing. It's going down. It's getting more negative. To get more negative, that is a gain of electrons, which by definition is reduction. You know, if you can't remember that, remember your mnemonic devices. Leo-ger, loss of electrons is oxidation, gain of electrons is reduction. Leo the line goes ger. So for the manganese, we see that we are gaining electrons. We are getting more negative, which means that the manganese was reduced. For the chlorine, we see that we're going from -1 to 0. We're getting less negative, which means that is a loss of electrons, which is loss of electrons is oxidation. So we've identified the oxidation and the reduction processes. Now we need to get into the oxidizing agent and reducing agent. And remember, the oxidizing agent and the reducing agent, these are the substances that force the oxidation and force the reduction of another substance. So we are looking for reactants. Generally speaking, they are not elements. They are not products. Now, some rare occasions exist where they are elemental, where You know, we're dealing with iron reacting with something to give it electrons or something along those lines. But that's not the same thing. We're not going to identify manganese or chlorine here as the oxidizing agents or the reducing agents. Reduction leads us to an oxidizing agent. Oxidation leads us to a reducing agent. The oxidizing agent is the one that contains the manganese. So that would be the permanganate ion. And the reducing agent would be the thing that contains the element being oxidized. So that would be the chloride ion. All right, any questions this far into the process?
Nope.
Okay, so we've met the first objective. We've assigned oxidation numbers. We've determined oxidizing agent. We've determined reducing agent. We know where the electrons are going. That's one possible question. And again, this would be if we saw a multiple choice question, this would be the kind of thing we would see in the multiple choice section. It is unlikely we would see this in the short answer section. Short answer section, we would see the balancing. Now, we can use this information to help us with the balancing as well. So if I take it from this perspective, I'm going to wipe out some of the information here. As far as information is concerned, we have two ways that we can go with this. We can use those oxidation numbers, figure out the movement of electrons, and kind of take it to the next step using the redox method that I taught you in lecture. Or we can break these into half reactions, solve each one of them individually according to the procedure, and then go from there. And so in the interest of completeness, I'll show you both methods, starting with the half reaction method. Even though it's not my favorite method, I do know that probably more of you use it than not use it. Just based on what I've seen in the equation balancing proficiencies. So what we would do in this is we've got the main idea. We know what's going to be oxidized. We know what's going to be reduced. So we're going to split that into sections here. We've got the oxidation reaction, where the chlorides are being turned into chlorine. And then we've got the reduction reaction, where the permanganate ion is being turned into manganese 2+. Now, if you assigned oxidation numbers already, then you've got one thing going for you. And that one thing is, you know how many electrons are going to be added to this reaction, and you know where they're going to be added. And the reason you know that is because by virtue of this being an oxidation reaction, Oxidation is the loss of electrons, remember? And so that means that electrons are going to be given away and show in the products as a result. And I also know that there are going to be 2 of those electrons. Why 2? Well, we know that every chlorine goes from a -1 to a 0 state. That's 1 electron that's disappearing. I have 2 chlorines that are doing that. So that means that there are 2 electrons in total that are being given away. From the perspective of this oxidation half reaction, I have no hydrogens. I have no oxygens. The only thing that is being changed up here is our charge. And we've just taken care of that with the 2 electrons. So our oxidation half reaction is now set. We're done with it. It's good. For the reduction half reaction, now we have to go into our procedures. Now, one thing that we do know is that in going from a state of 7 to a state of 2, 5 electrons have to come in. So we can put those 5 electrons, I know it's out of order to talk about it this way, but since we already did our oxidation numbers, we know that this is the case to begin with. 5 electrons are going to be going into the manganese to turn it from a +7 state to a +2 state. The battle is trying to figure out where everything else is going. And remember, there's a process here. We balance the oxygens with water molecules, and we balance the hydrogens in water with hydrogen ions on the other side. So I have 4 oxygens here. I'm going to need 4 water molecules to balance them out. And on this side, 4 times 2 is 8. I'm going to need 8 hydrogen ions to balance out those hydrogens. Does the 5 electrons work? Well, do we have charge balance on both sides? I've got a -1 here. -1 plus +8 is +7. +7 plus -5 is +2. So +2 on the permanganate side, +2 on the manganese and water side. They are balanced out that way. So I've got a balanced half reaction here. And so now from where I'm sitting, I've got 2 balanced half reactions that if I added them together right now, what I would get is something that's problematic. I would have 2 chlorides and permanganate and 8 hydrogens and 5 electrons turning into chlorine and 2 electrons and manganese 2 and 4 waters. This would be what I have as this is going. Now notice that I've got electrons on both sides, so I'm going to need to do some canceling. 2 of those cancel out. 5 minus 2 is equal to 3. So this would turn into this as my final reaction. Now there's a problem with this, obviously. I've got leftover electrons. Where are these 3 electrons going to come from? we can't have any leftovers. So to fix this issue, we're going to have to address the issue up here. We've got to make sure that every single electron that is given up by chlorine is taken in by manganese and vice versa. So 2 and 5 are my factors here. I need the lowest common multiple between them, which you can always estimate as the product of the two numbers, which would be 10. Sometimes it's lower than that, but 10's a good starting place. Multiplying them together is a good starting place. If I do that, that would mean that I need to take the top equation and multiply it by 5. I would need to take the bottom equation and multiply it by 2. And if I do that, for the oxidation reaction, I get 10 chlorides becoming 5 chlorines and 10 electrons. On the reduction side, I would get 2 permanganates and 16 hydrogens and 10 electrons to become 2 manganese, 2 plus ions, and 8 waters. So if I draw lines through my starters, when I recombine them now with the new numbers, it would be 10 chlorides, 2 permanganates, 16 hydrogens, 10 electrons, 5 chlorines, 2 manganese, 2 ions, 8 waters, and 10 electrons. Now I can see that my 10 electrons here and here are even and opposite, so they cancel, which leaves as a final reaction ten chlorides plus 2 permanganates plus 16 hydrogen ions make 5 chlorines, 2 manganese, 2 ions, and 8 waters. We can check for charge balance just as a way of kind of checking, make sure that we've got everything in the right places. 10 negatives from the chlorides plus 2 negatives from the permanganates make 12 negative. Plus 16 positives from the hydrogen ions would give a total of positive 4 on the reactant side. 2 positive 2s to give a positive 4 for the product side. Everything else is uncharged. I've got positive 4 on the left side, positive 4 on the right side. It's balanced. So obviously this is a much more involved problem, especially if you are a half reaction user. Now, if you're not a half reaction user, the path to The path to finishing this problem and making sense of it is a good bit easier. So again, here's where we started. We identified that the manganese was going from +7 to +2. That is a 5-electron process. We also saw that the chlorine was going from -1 to 0. But there were 2 of them going through that process, so 2 electrons were involved overall. From here, we would look at this and say, okay, manganese needs 5 electrons coming in, chlorine only gives away 2. Here's where we do the lowest common multiple between them. So we are going to multiply the manganese half reaction by 2, the chlorine half reaction by 5. And so 5 times 2 is 10 for the chloride. 5 times 1 is 5 for the chlorine. 2 times 1 is 2 for the manganese 2 ion. Now that we have this as our functional state, remember the next step is to go for charge balance. So I've got 2 -1s for permanganate and 10 -1s for the chlorine. That is a total of -12. On this side, I've got 0 for the chlorine and 2 +2s for the manganese. So that is a total of +4. It doesn't say if we're in acid or base, but we are going to assume it's acid. So I've got a difference here of 16. -12 and 4 are 16 apart from each other. Since this is acid, we're going to be adding positives, which means I'm going to need 16 H pluses to turn the +12 into a +4. So the 16 H plus ions go here. And then to counterbalance it, I would need 8 waters on the other side to balance out the hydrogens I just added. Waters don't add any charge. They just add elemental balance. And so I can double check myself. I know it's charge balanced already. I've got 16 hydrogens here. 8 times 2 is 16 hydrogens there. I've got 2 manganeses here, 2 here. I've got 8. 2 times 4 is 8 oxygens. I've got 8 oxygens in the waters. And I've got 10 chlorines here, and 5 times 2 is 10 chlorines as well. So we arrived in the exact same location, just 2 completely different ways. And so, balancing redox reactions, it's a longer type of question, but it is a fair game. It is something that you could see in that short answer essay section. And so what's really important there is if you see something like that in the short answer section where it's going to be on grade scope, you have to draw out as many steps as possible so that you can earn that partial credit if you're wrong. You know, figure out all of the oxidation numbers. I assign partial credit for assigning oxidation numbers correctly. If you do the half reactions, write out your half reactions. You know, if you have one of them correct and one of them incorrect, that's worth something. That's worth, you know, probably about 50% credit at minimum. So now, depending upon what other things you do, if you do this method here, you know, show your process, show where you got your numbers, and then how you use those numbers to get to the final answer. Because if you can show me that your logic is correct, even if your numbers are not correct, that is worth points. You know, I am all about giving credit for instances when you show that you understand the process, you know what you're supposed to do from a step-by-step perspective, but somewhere along the way you made a mistake somewhere and you just didn't know that you made the mistake. You know, if you do something silly like, you know, manganese is +6 instead of +7, and you did everything right after that step, well, guess what? You're going to get the majority of the points on that problem. You're not going to get full credit because you didn't do it fully correct, but you're going to get the majority of the points because after that one little mistake, you did fine. You did everything else that you're supposed to the way that you're supposed to. And that's why we're doing the grade scope part of this, to give you the opportunity to get those points back. Especially in circumstances like that where it is literally just one little mistake, or, you know, as we've seen on a number of occasions, significant figures, where, you know, you did all the problems right, but you got all the sig figs wrong, and you should have got like a 9 out of 10 on the quiz, but you got a 1 instead. You know, those kinds of things happen with Blackboard. That's why we go through and evaluate things as they're coming. Any questions with this example? We kind of took the long way to it.
No, I don't think so.
All right. So, all right, do we want to do another redox style question? Maybe not in as long form.
I had a real quick question. So the example final exam that you have, the practice one,
okay.
is that a good indication of what types of questions will be, like a good type or indication of what chapters we should study for? I mean,
the fall 15 exam, that one.
yeah.
So yes, that one was written before we did multiple choice in the final exam. So you know, let me share this so everybody can kind of see what we're talking about. All right, so these kinds of questions are, so this kind of question here, the protons, neutrons, you're going to see this kind of questions. This is probably going to be a multiple choice kind of question, where instead of having you write all this stuff out, it'll be something along the lines of, you know, what family do we find fluorine in? Or what's the most common charge on an oxygen atom? You know, what would be the expected charge of calcium? So you might find something, you know, with the protons, neutrons, electrons, that might be a fill in the blank kind of question because that's really easy. But in general, you know, a question like number 2, is prime for that kind of thing in the concept-based questions, because a lot of these are concept-based. You know, and you saw in some of the quizzes, you know, what is the element in the fourth group or in the fourth period that is a halogen? Name the noble gas in the second period. Name a metalloid in group 15. You know, those kinds of questions would be very easy to convert to multiple choice. You know, electron configurations, kind of the same thing. That's probably a pretty good multiple choice question. Especially since formatting those in Blackboard is ridiculously difficult to do. Here's an empirical formula and molecular formula problem. Good chance that you'll see something along those lines if it's there in the free response. Already talked about questions like number 6 gonna be in the free response for certain. Questions like number 7, probably in the multiple choice. Nomenclature would definitely be in multiple choice if it's there at all. Considering we did a whole bunch of proficiencies on that kind of material, I would expect that you're not going to see too much nomenclature there. Yeah, so I would say that this is probably not a terrible representation. I don't know if it's complete, but it's probably not bad. You can see we kind of hit all the major highlights. You've got questions in here about concentration. You've got questions in here about colligative properties like freezing point depression, boiling point elevation, osmotic pressure. You've got gas laws questions here involving, you know, the common gas laws like Boyle's, Charles combined. This one in particular here, you need to use the ideal gas law for. Here's a phase diagram question from out of chapter 6. Here's a stoichiometry limiting reactant problem. Wouldn't be surprised at all if you saw something along those lines. Here's a intermolecular forces problem about the differences between ethanol and ether and what we would expect their properties to be and why we'd expect them that way. You know, general questions here about polarity and bond strength. These would be really good kinds of questions to see in the multiple choice. So, you know, anything that you kind of look at it and go, huh, there isn't a whole lot of meat to that. I don't need my calculator to solve this. Those are the kinds of things that, you know, we asked as questions here because we gave a completely open exam in terms of there were no multiple choice questions, but those kinds of questions would be likely multiple choice questions now. So does that answer your question? I mean, this is a good representation. Now, equally good in that regard, you can see that the old exam review so the other one, this one, has a lot of the same kinds of concepts in it. There's nomenclature, there's configurations, there's redox, there's Lewis structures, limiting reactants, empirical formulas. You know, here's a Graham's law kind of question out of the gas laws chapter. Here's some general mole concept questions. So this was actually the review that I gave for that fall 15 exam. So that's why you can see there's a lot of similarity between the two. If you're looking for some multiple choice kinds of questions, just to kind of get a sense of what those multiple choice questions might look like from a concept standpoint, I would turn your attention to that ACS exam prep, the PDF that I put in there. Now, some of these, the thing you have to know about the ACS exam is that it is all multiple choice. There is no open-ended section to it whatsoever. So there are some calculation questions in there that would not be the kind of question we would ask you. But if you wanted to look at something like, here's a nice concept question that covers material from chapter 2 and chapter 21, asking about being isotopes and isoelectronic. You gotta know what both of those terms mean. The answer there, by the way, is B. In order to be isotopes, they have to be the same element. They just have to have different mass numbers. And since they're isoelectronic, they also have to have the same charge in this case. So some of those, for example, those two are isoelectronic. They both have the same number of electrons, 18, but they're not isotopic because they're two different elements. But you can kind of see in this review that there are a lot of concepts in here. And this is broken down into groups. So the reason why all of these questions seem to be asking the same kind of concepts is because the ACS review is thematic. They break it down by subsection. So all of these first questions are all about atomic structure. All of these questions are about bonding. So probably not going to be a whole lot of questions in here, just because a lot of these are going to require molecule drawing, and in order to do things like determine molecular shapes and that kind of stuff. Again, stoichiometry, probably not going to ask you any of these kinds of questions because you can see all of these are calculation oriented, with notable exceptions. So, a question like number 48, that's a possibility because that's just do you understand what a mole ratio tells you? Do you understand in number 49 what a limiting reactant is? So, for the multiple choice, for those 28 questions, this wouldn't be a bad resource just to get some practice in terms of the level and the kind of question that you could be asked for those. Again, avoid anything that's going to require significant calculation. That's not going to be there. But it wouldn't be surprising whatsoever if you got questions, like, excuse me, questions like, number 57, or like number 55. So, look out for some of those. Now, some of these, again, this is a national exam. There are some laboratory things that are woven into it. So you're not going to necessarily know all of these, but Yeah, I did provide you the key to this. So if there's anything specific that you're kind of like, "Oh, I really don't know the answer to it," check out that key. And if you can't reason your way to the answer on the key, send me a message. I'll try to kind of walk you through to the answer. Right. So any other questions I can answer for you right now?
I have a question. Going back to the redox reactions.
Okay.
I just don't know what to do whenever you have to balance it, balance water on both sides of the equation.
Okay, so if you're doing the half reaction method, when it comes to that step, so let's go back to the whiteboard here. What we did with the electrons here, you would have to do with the waters and the hydrogens on both sides as well. So anything that is common on both sides, you're going to need to reduce down by subtraction. So let's see if I can, yeah. Didn't want to do that, so I was trying to avoid. Okay, so if this was our final reaction right here, well, you could see from this that I've got electrons on both sides. I've got electrons here, and I've got electrons here. And I would have to cancel those out before I could finish this off. And so if I had waters on both sides, I would need to cancel out some of the waters. If I had hydrogens or hydroxides on both sides, I would need to cancel those out as well. Now, if you do it by this method, you shouldn't ever have to run into that, because the only time that you're adding hydrogens is to balance charge. The only time you're adding waters is to balance hydrogens. But if you do it with the half reaction method, there is a possibility, a pretty good one, that you would have multiple substances of the same kind on both sides. And what you need to do is basically reduce them. So I have 5 electrons on the left side. I have 2 electrons on the right side. Those 2 electrons are going to go away. And I'm going to turn that 5 into a 3, because 5 minus 2 is 3. And so that's what I would do. And so if I had waters on both sides, I would subtract the smaller number of waters from each side. That means that the one side would be completely canceled out, and I'd have however many are left over after the subtraction on the other side. And the same thing would go for the hydrogen ions as well. All right, does that make sense, Jasmine?
Yeah. So if I had like 3 waters on one side and then 6 on the other, you would just subtract it and have 0 on one side and then 3 on the other?
Yeah, that's it. That's exactly
That's
right.
all. And then you'd have to do the same thing with the hydroxides, or no?
If you have hydrogen or hydroxide on both sides of the equation, you'd have to do the same thing.
Okay, thank you.
You're welcome. All right. Other questions that need answered?
Could you explain a little bit what the ACS final is?
Okay, so in ordinary semesters, we would be having you take the American Chemical Society's national exam for General Chemistry 1. We do that as a way of kind of standardizing ourselves by comparing our results here at VU to other campuses and colleges in the state and nationwide. Now, in that scenario, we would be going off of a very different kind of grading system than what you're going to see tomorrow. That exam is 70 questions, and you get 100 minutes, I think. It's all multiple choice. The average score on that 70 question exam is something like, it's either like 39 or 40 out of 70. So obviously we would be grading that on a very, very different scale. We end up having, it gets complicated to explain exactly what that would mean for you. But basically we would be going in with the understanding that, you know, if you do well, if you score above the average, you're going to be okay. Now, obviously we're not doing that. But the reason I kept that stuff on there was, you know, I wrote the multiple choice section and I wrote it in a style similar to those, maybe not to the same depth of difficulty as some of those questions are, but I wrote it to a very similar kind of style, which is the same kind of style for all of your multiple choice questions throughout the semester. So it shouldn't really be that different for you in terms of that, but that's where that comes from. That is the national exam. And for those of you that are moving on into Chem 106 next semester, at the end of that course, you will take the national chemistry exam for first year chemistry, which would include all concepts from this class and from the next class, for the same purposes. It kind of keeps us on track, and since most of you transfer to somewhere else, it lets your transfer institution know that we're teaching you something.
So it's not something we're going to be doing this semester.
No, we're not doing it this semester. The ACS is a secured exam. It needs to have a live proctor, and Proctorio does not count as such a proctor. It needs to be taken in person in a classroom with a real instructor. So that right there disqualifies, well, pretty much the entire country from taking that exam. All right. Other questions?
I did have one quick one. Will there be anything about bond enthalpy on the final?
Not from the standpoint of you having to calculate delta H's. What you should know about bond enthalpy are kind of the general concepts that we discussed in chapter 4. So the difference in bond energy between a single bond, a double bond, and a triple bond, in terms of, you know, which one is more energetic, and, you know, the general trends related to atomic size. So knowing that when those two atoms are further apart from each other, the bond between them is weaker.
I have a quick question.
All right, go ahead.
I joined late, so I'm not sure, like, if you probably discussed this before, but did you mention like how many questions would be on the final?
I did. I'll put in a cheap plug while I show that first slide again. If you did come in late or have to leave early, the session is being recorded and will be posted to YouTube later today. So, you know, please pass that around in the event that you had to leave or you had to come in late. And the first thing that was discussed in The first hour was the parameters of the exam itself. All right.
Okay, thank you.
You're welcome. Other questions? Okay, so we can go in one of two directions with this. If we don't have anything specific to talk about, we can always, we have the option, we can end it right here. Or if we just don't know what to ask and we just want to kind of go over some general problems from a concept perspective, we can pick one of the old exams and kind of just walk through it, do a couple of questions off of it, and we can go right up to 4 o'clock doing that. All right, so if you're interested in leaving, go ahead and just do so now. If you want to stick around and go through some extra problems, go ahead. All right, we lost a couple there. That's okay. All right, so let's do this. Let's go back to that ACS exam. Let's do a couple of conceptual things. We'll take maybe 20 minutes and go through some conceptual problems, and then we'll pick on the fall 15 exam for the other 30 minutes and work off of that. So if you have access to it, I would encourage you to go ahead and pull this up. And we'll just do a couple of examples out of each of the subsections, at least for things that we might actually see tomorrow in the multiple choice section. And so what I'm going to need from you here is everybody pull up your chat if you don't have it handy already. Since this is multiple choice, it's going to be very easy to interact here. All I'm going to want from you is just a simple, ABCD once we go through the question, just to kind of see where everybody's head's at. So let's look at number 1 here. Number 1, we've got an atom of strontium-90. What is its composition? What's in strontium-90? Give me an answer, A, B, C, or D, and do it now. Okay, looks like everybody's in the same neighborhood. We're all saying A. A is correct. Now, where did that come from? Well, you had to have a periodic table somewhere around on you to do that. And so if you did that, what you would see is that strontium SR is element number 38. So since it was an atom, that means it had 38 protons and 38 electrons. The 90 in that problem was referring to its mass number. So its mass number of 90 would mean that it had 38 or 90 minus 38, which would be 52 protons. That is A. Okay, gonna do things a little bit differently this time. For question 2, I'm gonna try to push a poll out to you. All right, go ahead and now you can't see what everybody else picked. All right, so what do those 3 nuclides have in common? All right. All right. All right, only half of you have put in. Make a guess. Doesn't have to be right. Okay. Okay, so this is where we were. Most of us chose C. A few of us chose B. C is the correct answer. These are isoelectronic. Again, coming to the periodic table, neon is atomic number is 10 with no charge. It would have 10 electrons. Fluorine's atomic number is 9 with a -1 charge. It would have 10 electrons. Magnesium, atomic number 12 with a +2 charge. It would have 10 electrons. All 3 of them have 10 electrons. The answer is C. All right. All right, let's go again here. Number 3, which pair here represents isotopes? So what does it mean to be an isotope? All right, it's looking pretty good. Almost everybody's in. And everybody is correct. B. Uranium-235 and uranium-238 are isotopes. Both are isotopes. Remember, to be an isotope, it has to be the same element with a different mass number, meaning a different number of neutrons. All right, let's look at number 4. This is a nuclear chemistry question. Which particle, if lost from the nucleus, would not change the atomic number? Go ahead and think on that one. Put in an answer. All right. Almost everybody's in. All right, so before I tell you the correct answer, we did have a little bit more of a split here than usual. The correct answer is D, the neutron. Now, why is the neutron not going to have an impact on the atomic number? Well, of these 4 particles, it is the only one that does not have a charge. And since all of the charges are going to be gathered or lost from the nucleus, any charged particle that comes out of the nucleus is going to have a change in the atomic number that comes with it. The neutron has no charge. So neutrons will not change atomic number. And neither will gamma radiation. Gamma radiation will not change the atomic number either. But proton decay, alpha particles, beta particles, positron emissions, all of those would result in a loss of, or a change in the atomic number rather. All right, number 5, a great chapter 2 kind of question. Let's see where we're thinking. What do we remember from atomic theory in chapter 2? Okay, we're mostly in the right headspace. The key word in this particular problem was passing through without any major deflection in path. The fact that most of them passed through without deflection was an indication of the fact that it was mostly empty space. That's what I see is correct. D is very, very incorrect. D, alpha particles do not have a lot of penetrating power. If you remember from the nuclear video, alpha particles have the least penetrating power of the radioactive particles. They can be blocked by your skin, your clothes, and most other objects. So they do not have a terrible amount of penetrating power. All right, let's look at number 6. Number 6 is a good electron configuration concept question. All right. D is the correct answer. Those of you that picked C, don't feel bad. It's a very common mistake to get those two mixed up because they sound so similar. Remember, the alkaline earth metals are group 2. So they would have a configuration of NS2. S2 would be their last configuration, not S1. All right, let's look at number 7. Energy of a photon is greatest in the case of okay. For this one, you had to remember your electromagnetic spectrum. What light has the most energy? What light has the least energy? So X-rays would be the greatest energy. They have the lowest wavelength, the greatest frequency. Infrared would be on the opposite end of the spectrum. It has high wavelength, low frequency, low energy. So A is the correct answer there. All right, let's skip ahead a little bit. Let's look at 18 and 19 here. So 18, which emission line would occur at the highest frequency? So which emission line is going to have the greatest energy? Now, the key to this question, is the understanding that as we get further from the nucleus, the energies of those spectral lines, the energies of those energy levels, get closer and closer and closer together. So the gap is biggest between the first energy level and the second. Once we go from there, the third energy level is a little bit closer. The fourth energy level is a little closer than that. The fifth is a little bit closer. The sixth is a little bit closer than that. As we get further from that nucleus, the energy levels kind of start to cram together a little bit more. It's also the reason why we see in electron configurations so much meshing between the energy levels in terms of where the electrons are, because we know that not only are the energy levels getting closer together, the SPD and F orbitals that make up those energy levels vary widely in their energy as well. And so that's for that reason we see that the 4s orbital is going to be lower in energy than the 3d. The energy levels are close to each other to begin with. And when we take the lower energy state of an s orbital compared to the higher energy state of the d sublevel, there's a reason why they kind of switch places a little bit there. So the answer there is A. The highest energy emission is going to be from energy level 3 to energy level 1. That's going to be where we have the biggest gap in energy because of how far apart those first few energy levels are from each other. And the lowest energy transition actually will be the D from 10 to 8. All right, let's look at number 19. Number 19 is a good quantum numbers kind of question. If n is equal to 4, which set of quantum numbers would be correct or could be correct? right, there's a little bit more hesitation with answering this one than the others. And it's understandable. This is a concept that we haven't talked about directly since we first looked at it in chapter 3. Now, the 7 of you that put in your answers, you're correct. A is the correct set of numbers, or a correct set of numbers. Remember our parameters. L can be anything that is an integer, a whole number, starting with 0 and going to n minus 1. So since n is 4, L could be 0, L could be 1, L could be 2, or L could be 3. So from that perspective, all of the options are okay for L with the exception of B. B, we would eliminate automatically based on its value of L. L cannot be equal to N. It has to be at least 1 lower than N. M sub L can be anywhere from positive L to negative L. So from that perspective, since L is equal to 3 in this case, -3, -2, -1, 0, 1, 2, and 3 would all be possible. So far, so good here. This would not work for letter C. M sub L cannot be positive 3 if L is only 2. D would be okay. The last one, spin quantum number. Spin is either going to be positive 1/2 for spin up or negative 1/2 for spin down. 1 is not a possible value there. 1 would be eliminated. That gives us A. Okay, before we move on to some calculations, let's go ahead and do a couple of questions here out of the states of matter, just to make sure we're kind of in the right headspace, that we get what we're doing here. So let's look at number 52. 52 should be a relatively easy question if we remember anything at all about phase diagrams. According to the phase diagram, what is represented by F? Zoom in a little bit on that phase diagram if I can. All right. Most of you are saying B, that it's liquid and gas. That would be correct. Just remember the region here to the far left and upper is solid. The region to the lower and right is gas. Liquid is in the middle. Anything on the line that divides them would be both at the same time. So F is on that line between liquid and gas, which means that it is both liquid and gas at the same time. Let's look at number 53. See if I can't scroll over a little bit. All right, let's end it right here. Most of you are on the correct answer of B. Now the keywords here, the keyword of normal melting points, normal boiling points are those that occur at 1 atmosphere of pressure. So for freezing point or melting point, we'd be looking at that solid to gas line, or solid to liquid line rather. So where 1 atmosphere and the solid liquid line meet is negative 15 degrees. That would be letter B. All right, one more out of this section. Let's look at number 54. Two substances, pure substances, A and B, each melt at 87.5 degrees Celsius. An unknown of pure solid substance X also melts at 87.5 degrees Celsius. Mixtures of X with A, X with B, and A with B are made, and melting points are determined to be below 87.5 for each of them. What is the true statement here? Okay. All right, this one we have to logic our way through. Now, the important piece of information is that each mixture was tested and found to be to melt below 87.5 degrees. Now, why is that significant? What does that mean?
If they were the same substance, then the melting point wouldn't change.
Right. If they were the same substance, then the melting point wouldn't have changed at all. If they were different substances and they were making a solution, which as they melted, they would have made a solution. That falls into the freezing point depression argument. So when I have a mixture of substances, their freezing point collectively will drop. That's freezing point depression. That is the definition of that colligative property. So the fact that all 3 mixture combinations all depressed in their freezing point, all froze at lower temperatures, indicates that none of the substances are the same. If none of the substances are the same, then C is correct. Otherwise, we would have seen one or more of the combinations have a uniform 87.5 degree temperature freezing point. So, this is a little bit of a twist on freezing point depression, but it's the same kind of idea. When we have a mixture, this is what we would expect of the mixture if it was in the liquid phase. All right. So there are others in here, but I want to give us a chance to do some calculation things. So I'm gonna move us off of here unless I hear some significant objections. We've got about 20 minutes left. That's time enough to probably do a couple of example problems. So if you have it handy, I would direct you to the final exam review from fall 15. Okay, so not that one, the fall 15 final exam. Okay, so we've done a lot of these. How do we feel about nuclear reactions? Question 10. Okay, we got one thumbs up from Jacob. No one else has their camera on, so I can't see them. Okay, Nikki says that we're okay. All right. All right. Do we want to do something else? I guess that's the more pressing question. Okay, I've got a request to do one. Okay. Okay, so the real key in these is, again, the separation. The mass numbers have to be equal on both sides. The atomic numbers have to be equal on both sides. And any plussing or minusing that we do has to be taken care of there. So if I look at this first one, I've got plutonium-239. So I've got 239 as my mass number on the reactant side, and it's turning into uranium-235. So I've got 235 as the mass number over here. All right, so from a mass number perspective, I'm going to ask you, William, since you asked for this problem, what is the mass number for our missing particle?
4.
It's going to be 4. That's correct. Okay. And on the atomic number side, I've got a 94 for the plutonium. I've got a 92 for the uranium. What is going to be the mass, or excuse me, what is going to be the atomic number on this side?
2.
2. All right. So we need to identify this particle. What is this particle? It has a mass of 4, a charge of 2.
Is it the alpha particle?
It is the alpha particle. And so we could write that here. Now, if you had written this as 4 to helium, in this particular case, that would be okay as well, because helium does have an atomic number of 2. That would be okay. As far as nuclear reactions go, these two are synonymous. But there's only one correct answer for the name of particle. You have to call it an alpha particle. You cannot call it a helium particle. In the second problem, now we're dealing with a neutron bombardment. We've got uranium-235 being hit with a neutron to form cesium-144, rubidium, or cesium-141, rubidium-92, and 3 something else's. So we do the same kind of thing here. 235 plus 1 gives us a total of 236 for the uranium, for the reactant side rather. 141 plus 92 gives us 233. So if we looked at from this perspective, I would need 3 as a mass number over here. On the atomic number side, 92 plus 0 is 92. 55 plus 37 is also 92. And so there'd be no charge. So in total, I need a total mass number of 3, a total atomic number of 0. Since there are 3 particles here that we're told about, each one would have a mass number of 1, atomic number of 0. We call that particle a neutron. So we would call those neutrons. Very, very similar to the problem that we did in class together on, I guess it was Friday, out of the post lecture. Okay, let's look at one more kind of problem, unless there are questions about this one. All right, I've already did one of those. Okay, let's look at number 13 here. The boiling point of ethanol, the structure on the left, is 78.37 degrees Celsius. The boiling point of dimethyl ether, which is also C2H6O, is negative 24 degrees Celsius. Given those Lewis structures, why is there such a difference in the boiling point? So before we get to that, can anyone tell me the term for two substances that have the same molecular formula but different structures or configurations? Okay. All right. It's a good guess, Andrew, but it's incorrect.
I want to say isomer.
I want to say you're correct. Okay. The correct term is isomer. These are, in fact, what we would call structural isomers. Two substances with the same molecular formula, but completely different ways of arranging the molecules. Resonance, yeah, to Andrew's point, resonance is when we have the same structure, but we've got a double bond that is able to move. So we have two different ways of drawing the same structure as opposed to two different structures from the same molecular formula. That's the difference between them. Okay, so that being said, I'm assuming the way that Jacob's looking at me, he knows the answer. Let me see if anybody else knows the answer. Why is there over a 100-degree difference between the boiling points of these two substances, despite the fact that they have the same molecular formula? All right, throw out an idea. Even if you don't have the whole thought, throw out an idea. Okay. Difference in intermolecular forces. We're on the right track. This is an intermolecular forces problem. What are the differences? Why are they significant? It's not about surface area. Surface area really only comes into play specifically if we are dealing with London forces only. While both substances have London forces, that is not the most significant factor. Okay, Andrew, expand upon that, please.
So the first one has like, ethanol has a hydrogen bond to an oxygen, whereas dimethyl ether has that hydrogen bonded to a carbon. So I'm guessing it's just like an extra hydrogen bond.
Okay, so yeah, remember, hydrogen bonding exists between hydrogens and either oxygen, nitrogen, or fluorine.
Okay.
So carbon to hydrogen bonds are not hydrogen bonds. They're in fact pretty much non-polar bonds in entirety. The main factor there is that we've got a hydrogen bond here. And that hydrogen bond, because of its increased polarity, is going to have a greater attractive force. Those ethanol molecules are going to stick together way more than the dimethyl ether molecules will. Now, it's important to note that oxygen in the middle there is significant. It does create a polar center. Dimethyl ether is polar. It does exhibit dipole-dipole forces. Basically, anytime we see oxygen or nitrogen in the middle of a substance like that, it's going to cause a bend in that substance that is going to allow for polarity to kind of congregate, the negative charge to congregate around that negative center, that oxygen. But the lack of hydrogen bond there is going to mean that the forces are going to be weaker overall. So, the reason for the high boiling point in the ethanol is that hydrogen bond there. Okay, we've got about 5 minutes to go. I'm gonna cut our review there. So a couple of things that I want to encourage you to do. First and foremost, obviously, if you have not passed all of your proficiencies yet, today is the last day to do so. If you can't pass those proficiencies tonight, it doesn't matter how well you do tomorrow. So that's the first thing. The second thing, go ahead, make sure that you give yourself an opportunity to do those pre-checks for the exam. Go to the exams area, do the pre-checks. That's not a graded item, but it's going to give you a score. The score is complete nonsense. But it is going to let you know if you need to make any updates to your computer, if your computer is running optimally for the exam. It's going to greatly reduce your stress and anxiety tomorrow to know that you've already kind of gone through the proctorio rigmarole once and should be able to go through it again pretty easily. So if you haven't done that yet, make sure to do so. Now, again, if you've been doing the proficiencies and whatnot, you've probably already done all of that stuff anyway. You should be okay. Third thing, the official test time is 6 to 7:45 tomorrow. However, couple of things. First of all, I am opening the test up 10 minutes early. So it will be available at 5:50. That's to allow for some of those pre-checks to take place, so that in the event that you get hung up on something, you have a Wi-Fi issue, whatever the case is, you've got 10 minutes to kind of figure that stuff out. If you hit begin in that 10-minute period, the exam will start. You will have an hour and 55 minutes from that point in time. So the exam will be over somewhere around 7:45, 7:50, depending upon when you hit that begin button. Once you finish the exam, you need to take all of that stuff from question 29 on and move it over to Gradescope. So don't just do the stuff in your head. Make sure that you're writing everything down so that it can be very quick picture, 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 and throw it up onto Gradescope as you go. If you finish early, obviously port that stuff over to Gradescope early so that you can be done. One thing that happened last night that you should be aware of, I had a couple of students that through Wi-Fi connectivity or something, basically they started working through the exam, went to hit submit, and found out that they had been logged out and didn't even know it. So one thing that I would encourage you to do is just periodically make sure that you're still there. If you see that your answers are saving, every so often hit that refresh button just to make sure that you're still in Blackboard. If you happen to get kicked out of Blackboard, let me know about it. I'll try to check your progress, see what has been submitted and what hasn't been. So long as your exam has not been submitted yet, you should be able to re-access and get back into the exam itself. What happened in the case of those two students last night is basically the exam was still open and they never actually submitted it, even though they clicked submit because they weren't logged in. And so they had to go back, and in an unfortunate case, one of them had to more or less redo 2/3 of the exam, but she had plenty of time left, and so she was able to do it. So make sure that you're doing things on your end, and if you need something, if something comes up like that was a really big issue that came up last night and needed immediate attention, I am available to you starting about 5:45 and going all the way to about 8 o'clock or so. I'll be on Remind. I'll have access to email as well, but obviously you all have my Remind. Easiest way to send me a question is through there. I'll be checking both, but obviously the text message is going to come through faster than the email is. Does anybody have any questions?
We only turn in our calculation problems to Gradescope, right?
That is correct. All the multiple choice are going to be locked in to Blackboard. So whatever grade you get there, there's no partial credit.
Okay, thank you.
You're welcome. All right, anything else? All right, thank you for coming in and spending your afternoon here. I do appreciate the time that you're putting into this. Good luck tomorrow.
Thank you. Thank you for the help.
Thank you.